Welcome to Unit 9. These are notes 9.1 on acids and bases. As you can see over here, we have some very common household chemicals, food that we eat. The main properties of acids, which are substances that have a pH lower than 7, so are in this diagram that we have down here, those are the substances that are over here on the left of the diagram. The main properties of the acids is that they taste sour, for example. So lemon tastes sour. Please don't taste anything to know whether it's acidic or basic, but lemon tastes sour, tomato tastes sour, okay? And another property of acids is that they turn litmus paper red, okay? So they change the color of the pH paper. And those are the main properties of the acids. The main properties of the bases, which are the substances that have a pH higher than 7, so if we look at the diagram, anything that is to the right of the number 7, that's going to be basic. The main properties are they taste bitter. And again, please don't taste things to know what their acidity is or how basic or acidic they are. And they feel slippery, lots of them. And then also they turn red, litmus paper blue. So what are examples of basic products? Basic products are soaps, for example. Any cleaning product is a base. Okay, so maybe you want to check at home and then classify some of the products that you have home and some of the substances that you have home and look at this diagram over here and understand whether they fall into the lower than 7 scale or higher than 7 scale to know whether they're basic or acidic. So how do we understand what's in chemistry an acid or a base? What is an acidic solution or what is a basic solution? We need to look at the ions in that solution, okay? So it says over here, relative amounts of hydrogen ions and hydroxide ions in aqueous solutions determine whether solutions are acidic, basic, or neutral. In the first place, hydrogen ions are expressed like this. These are also called protons, okay? Hydroxide ions are the OH negative ions that you see here that you have probably seen throughout the year because this is a polyatomic ion, okay? When we have an aqueous solution, that means that that's a solution that is dissolved in water. So what this means is that the amounts of hydrogen ions and the amounts of hydroxide ions that are dissolved in a solution of water, in an aqueous solution, will tell you, that amount will tell you whether you have a basic solution or you have an acidic solution. What's going to be an acidic solution? An acidic solution will be a solution in water that contains more hydrogen ions than hydroxides. And what's going to be a basic solution? A basic solution would be a solution in water that contains more hydroxides, so more OH negative ions than hydrogen. If our solution is neutral, I guess that you already know what that means. Neutral will mean that we have the same amounts or equal amounts of hydroxide ions and hydrogen ions in that solution. Okay? The water produces the same number of hydrogen ions and hydroxides. Okay? Water produces the same or equal amount of hydroxide ions and hydrogen ions. If we actually break the molecule of the water, which is the dissociation of the water, this is what we find. If we find out that the water breaks into H plus and OH minus. This is called the auto-dissociation of the water. To dissociate means to break, and it's used for ions. When we say that ions dissociate, that means that the ions separate. So this is the auto-dissociation of the water. The auto-dissociation of the water could be expressed that way, or can also be expressed the way you see down here. This is water dissolved in water. So it's pretty much the ionization of the pure water. When the water dissolves in water, it breaks into hydroxide ions and something that we call the hydronium ion. Okay, we call it the hydronium ion. I'm going to move this over here. The hydronium ion. The H3O plus ion has the exact same value has the exact same value as the hydrogen plus. So to see one or the other, it's gonna mean exactly the same. Okay, so you can express the auto-dissociation of the water, the breaking of the water, in two ways. You can use the one that we have up here, or you can use the one that we have down here. Both are valid. That is how the water breaks within itself. And it breaks into H plus and OH minus, or it breaks into H3O plus and OH minus, which is exactly the same. There is different definitions to explain what an acid is and what is a base, or what a base is. But there's two main definitions. The first definition is the definition of Arrhenius. Arrhenius defined the acids and the bases based on the amount of protons, the amount of hydrogen ions they had. So an Arrhenius acid, it's a substance that when you dissolve it in water, when it's in aqueous solution, when it's added to water, it's gonna increase the concentration of the protons, those ions in the solution. So for example, an Arrhenius acid would be considered the hydrochloric acid that we have over here, because, check the diagram that we have right here, because when hydrochloric acid it's dissolved in water, it breaks into hydronium, so H3O plus, and chloride, which is exactly the same as what we have up there. When the hydrochloric acid breaks or dissociates, because it has been dissolved in water, it would break into the hydrogen plus and the Cl minus, okay? So again, to express the dissociation or the breaking of the hydrochloric acid this way, or to express it this way, it's perfectly fine. It's the same thing, okay? And again, hydrochloric acid is an acid, it's an Arrhenius acid, because it's a substance that when dissolved in water, increases the amount of hydrogen ions, adds hydrogen ions to the concentration or to the solution. What's going to be an Arrhenius base then? Well, it's going to be a substance that when it's added to water, so when we have it in aqueous solution, when it's added to water, it's going to increase the concentration of the hydroxides, okay? So for example, based on Arrhenius' definition of acids and bases, in Arrhenius base, it's the sodium hydroxide. Why? Because when the sodium hydroxide it's dissolved in the water, it breaks into sodium and it breaks into hydroxide. So it adds hydroxides to the solution. Okay, so again, an Arrhenius acid is going to be a substance that adds hydrogen ions to the solution, and an Arrhenius base is going to be a substance that adds hydroxide ions to the solution. Now that we've learned the definition based on Arrhenius' criteria of acids and bases, so we're going to classify the following substances into acids or bases. Okay, so the first one is called nitric acid, but you don't need to know that name. So what you need to do in order to understand whether this substance is an acid or a base is you need to dissociate, you need to break the substance into the corresponding ions. To do this, you need to look at the periodic table, at the back of the periodic table, and look at the polyatomic ions chart. So if you look at the polyatomic ions chart, you're going to see how this substance is formed by a polyatomic ion, that is a polyatomic ion. This substance is formed by a polyatomic ion, that is a polyatomic ion that you've seen very often in the past, that is the nitrate, okay, NO3 negative. So if you actually check this out, NO3 negative, the only thing that is remaining to complement or to form this substance would be the hydrogen, so that is going to be the H plus, okay? So because this is a substance that breaks when it's dissolved in water, then you would have to write here aqueous and aqueous, because that is going to determine that the substance was dissolved in the water and it broke into the corresponding ions, okay, aqueous. And now, in order to know whether this is an acid or is a base, you check out the ions and you say, okay, is this substance adding hydroxides to the solution, or is this substance adding hydrogens to the solution? So it happens to be the H pluses, right? So because this substance is adding hydrogen ions to the solution, this is going to be considered an acid. Then we have another substance over here, lithium hydroxide, that if you again look at the polyatomic ions chart, you will see how it would break into hydroxide. This is the polyatomic ion, and then whatever is remaining would be the lithium plus. Lithium is positive because it's a metal, okay? So because this was dissolved in water in order to break into ions, the lithium hydroxide would be aqueous, the lithium would be aqueous, and the hydroxide would be aqueous. This only means that the substance was dissolved in the water to break into the ions. So now, if you actually want to understand whether this is an acid or a base, you need to look at whether it is releasing or adding hydroxides or hydrogens to the solution. So because this one is adding hydroxides to the solution, we consider this substance a base. Now, next one. We look at the substance and we look at the periodic table, the back of the periodic table, and we identify the polyatomic ion. And the polyatomic ion that we have here is the SO4. And the charge of the SO4, you have it on the periodic table, is 2-. It's a sulfate. So what's left in order to form this compound, in order to form this substance? What we have left is 2 hydrogens here. So what you do is you write a hydrogen ion. You cannot do it with a 2+ because that doesn't exist. Hydrogen ions only have 1 positive charge. So you write the hydrogen ion. And now we balance and we see that we have 2 hydrogen ions, so you write a 2 here. So now we are going to analyze this as an acid or a base based on what they're adding to the solution. So if this is in the solution, again, this should be aqueous, aqueous, and aqueous. Okay, so because the substance is adding hydrogens to the solution, this substance is considered an acid. It's actually sulfuric acid. It's considered an acid. Okay, and finally, the last substance that we have over here, again, we break it into ions. So I'm going to write it here, okay? MgOH2. So we break it into ions. And when we break this into ions, we have to look at the back of the periodic table and understand what's the polyatomic ion that is taking place here. And the polyatomic ion that is taking place here would be the hydroxide. But check it out, we have 2 hydroxides there, right? So what we do is we balance this. We're going to do it in a minute, okay? So it's going to be 2 hydroxide because we have a 2 there. And then what's left? We have the magnesium. What was the charge of the magnesium? Well, magnesium is in group 2, so it has a charge of +2, okay? So 2 plus 2 negative charges, that would make the compound. Again, because this is dissolved in water, because it only breaks when it's dissolved in water, the 2 ions are going to be aqueous, dissolved in water, and the magnesium hydroxide is going to be aqueous as well, dissolved in water. And then finally, we see whether this substance is an acid or a base. So we understand that the substance is releasing hydroxides, so it's adding hydroxides to the solution. So therefore, this substance is going to be considered a base. There is another definition of what an acid and a base is, and is the Bronsted-Lowry definition of acids and bases, okay? So this definition says that an acid is going to be a substance, it's called a Bronsted-Lowry acid. It's going to be a substance that donates protons. So remember, protons are hydrogen ions, okay? A proton is the same as H pluses. So a substance that is adding or donates or gives protons away, that is going to be considered an acid, okay? And the Bronsted-Lowry definition of a base is going to be a substance that instead of donating protons, instead of giving protons away, it's going to be accepting those protons. So it's a proton acceptor. And again, remember, proton, it's a different way of calling the hydrogen ions, okay? The hydrogen ions are also called protons. All right, so I'm going to give you here an example of what would be an acid and a base based on Bronsted-Lowry's definition. So the first example that you have here is the NH3, Okay, when we dissolve the NH3 in water, because again, what we're doing all the time is we're dissolving the substances in water to see whether they're acids or bases. When we dissolve the NH3 in water, check this out. Check the molecules. We're going to open the molecules into their Lewis structures, okay? And what's going to happen is that one of the hydrogens, one of the protons that the water has, is going to go away. So the water is going to donate a proton, it's going to give away a proton, and that proton is going to be accepted by, is going to be taken by the NH3. So the hydrogen of the water, the H plus of the water, the proton of the water, is going to be taken by the NH3. So what happens afterwards? That is when you mix them together, the reactants. What happens is that now the NH3 has accepted a proton, and the water has given a proton away, so has donated a proton. Okay, so what is the aftermath of this? What happens is that once the NH3 has accepted the proton, it becomes NH4 plus, that is NH3 plus one hydrogen, so NH4 plus. And once the water has given away, donated that one proton that was given away, once the water has donated that one proton, now the water has one less proton, so instead of H2O, it's going to be OH minus, which is the same as H2O minus one proton. So again, a Bronsted-Lowry acid is a substance that gives protons away. In this case, it's going to be the water. And a Bronsted-Lowry base is a substance that takes the protons when it's dissolved in the water. So in this case, the base is going to be, for this example, the base is going to be the NH3. Okay, so when we have these situations where one of the two substances is taking protons and the other one is giving them away, when there is a proton acceptor and a proton donor, what we have, it's a reaction, okay, or it's a chemical reaction in which we have the base and the acid, and then the conjugated base and the conjugated acid. And I'm going to explain what that is right now. Okay, so the conjugate base of an acid is going to be formed by the removal of a proton from the acid. So, for example, in the example that I gave you before, the acid was going to be, or is the water, because the water is giving that proton away, okay? So now I go back to the same reaction here. The water is going to give the proton away, so the acid is the water, okay? So when the water gives the proton away, it becomes the conjugate base of that acid. Why? Because it's the consequence, or is the result of the acid losing one proton. The conjugate base is the result of the acid losing one proton. So it's formed by the removal of the proton from the acid. Now, what's going to be the conjugate acid? The conjugate acid is going to be the substance formed by the addition of a proton to the base. So in this case, if the base was the NH3, because we saw how the NH3 was taking that proton. So the base is the NH3. This is the base. When the base loses a proton, it becomes the conjugate acid. So the conjugate acid of that base is going to be the NH4. Okay? So again, when the acid loses the proton, it becomes into its conjugate base. And when the base takes the proton, it becomes into its conjugate acid. So a conjugate acid and base pair is going to be two substances, related to each other by either the donation or the accepting of the proton. Okay, so for example, in this case, H2O, that is the acid, and OH, that is the conjugate base, is a conjugate acid-base pair. And NH3, that is the base, and NH4, that is the conjugate acid of that base, is a conjugate acid-base pair. Let's understand some examples here so that we can actually better understand the idea of conjugate acids and bases. okay? So it says identify the conjugate acid-base pairs. So you have two substances that are going to be combined together, okay? One is going to be the acid and one is going to be the base. And after that, the acid is going to be coming to the conjugate base and the base is going to be coming to the conjugate acid. So let's see what we have. In the first case, we have HNO3 plus water. It's the hydronium, H3O plus, and O2 negative. So what has happened here? If you notice, the H3O plus is actually the water that has gained one proton. So where is that proton coming from? It's going to come from here. So that means that this substance is giving to the water one proton. So this substance over here is the proton donor. And then the water, in this case, because the water can act as an acid or a base, is going to be the one that is taking the proton. So it's the proton acceptor. The proton donor is what we always call the acid. Okay? And the proton acceptor, following Bronsted-Lowry's definition, is what we always call the base. Okay, so when the acid loses that proton, it becomes this substance over here, NO2 negative. So when HNO2 loses the H, it becomes NO2 negative. So the NO2 negative is what we call the conjugate base of the acid. So this is conjugate base of that acid. Now, when the water gains that proton, it becomes H3O plus. So the H3O plus, it's going to be the conjugate acid of that base. Next example, we have HCl and OH, and then that turns into H2O and Cl negative. So what has happened here? What you can see is that we have the Cl negative at the end, right? So the Cl negative at the end means that the HCl has given the proton to the OH to become Cl negative. So the proton has been given from the HCl to the OH. So the proton donor is going to be the acid. So the HCl will be the acid in this case. The proton acceptor is going to be the base. So the OH negative is going to be the base. Now, when the proton donor loses the proton, it becomes, in this case, chloride, Cl negative. So that is what we're going to be what we call the conjugate base of that acid. So this is going to be the conjugate base of the HCl. And when the OH gains that one proton, it becomes water. So in this case, the water is going to be the conjugate acid of the other base. So the water is going to be the conjugate acid of the base. And then finally, we have HCO3 negative plus OH negative. They become water and carbonate. Okay, so what has happened here? Carbonate is missing one hydrogen. That means that the HCO3 has given this one proton to the OH. So that means that the HCO3 negative, the bicarbonate is called, it's going to be the acid. That's the acid, the proton donor. The OH in this case, because it's taking the proton, is the proton acceptor. That's going to be the base. Now, when the acid gives the proton away, it becomes the conjugated base. So the conjugated base of that acid, is the carbonate. This is a conjugated base of the acid. Okay? And then when the base, which is the OH, gains one proton, the water is going to be, this is going to be the conjugated acid of the base. Okay? So again, in this case, the acid is HCO3, and the conjugated base of that acid is CO3 2 negative. And the base is going to be OH, and the conjugated acid of that base is going to be the water. Okay, so we're gonna see a couple of examples to understand how to find the conjugate base of an acid or the conjugate acid of a base. In this example 3, it says give the conjugate base of the following. So if you have to find the conjugate base of the substances, that means that the substances that they're giving you are acids. Okay, an acid, remember, it's a substance that gives protons away. Okay, it's a substance that loses protons. Okay, so if we make the HF lose one proton, the substance that we're gonna have is gonna be F minus. So therefore, the conjugate base of this acid would be fluoride, F negative. That would be the answer. Okay. Now, if we have H3PO4, and this is an acid because we're looking for the conjugate base, what we need to do is we need to make this substance lose one proton. So if we, out of the 3 protons that it has, if we remove one, the conjugate base of this acid is going to be H2PO4 minus. And finally, if we have the hydronium, the H3O plus, and we want to find the conjugate base of that substance, which is going to be considered an acid, we have to make the H3O plus lose one proton. So if we remove one hydrogen from that substance, what we're gonna have is H2O, because we're removing one H plus from the H3O plus, therefore the water is neutral. Now it's asking you to find the conjugate acid of the following. So to find the conjugate acid means that the substances that you're given are bases. And if they're bases, what you need to do is you need to add one proton to them because they're proton acceptors. Bases are that you're giving the proton to the substance, okay? You're giving the proton to the substance. So if you want to give a proton to bromide, Br negative, then you would add one hydrogen. So what you would end up having would be HBr. Now, if you have HSO4 negative, and that is the base, to find the conjugate acid, you would have to add one proton. And adding one proton would mean that you would be forming H2SO4, and that is sulfuric acid. Finally, if you have the carbonate ion, and that's the base, and you want to find the conjugate acid, would be the substance after adding one proton to the CO3 to negative, so that would be HCO3, one negative, that is bicarbonate. So now we're going to learn what is an acid that is strong and what's a base that is strong. Because being strong as an acid or being strong as a base is not the same as having a lot of protons or a lot of hydroxides. It's about being very easy to break or dissociate when you dissolve it in water or not, okay? So strong acids are acids that ionize completely, that break into their ions completely. And strong bases are bases that ionize completely. So it means that they are breaking absolutely into positive and negative ions, okay? So the key to be strong is that when they are dissolved in water, they completely ionize, they completely break into the corresponding ions. And that means because they break into positive and negative ions, they don't do it partially, they completely break into positive and negative ions. That makes them really good conductors of electricity, okay? Weak acids and bases only ionize partially, okay? So they only ionize partially, meaning that they break into ions, but their reaction goes back and forth. It doesn't just go in one direction and they break. The reaction goes back and forth. And because they ionize partially, they're going to be bad conductors or not good conductors of electricity. Okay? When we have a strong acid or we have a strong base, it is because how easy it breaks into ions, how easy it ionizes. So it's not because of how many protons it has or what the concentration of the protons is, okay? So being strong acids and strong bases is about, or being weak acid or weak acids or weak bases is about how well they ionize, how easily they break into ions completely or not. Examples of strong acids, you have them here. The hydrochloric acid, the hydrobromic acid, the nitric acid, etc. Examples of strong bases, you have them here. Examples of strong bases, you have them over here. You have the sodium hydroxide, the potassium hydroxide. Any hydroxide normally is going to be a strong base. So again, a strong acid is an acid that completely breaks into its corresponding ions. It completely dissociates. And a strong base is a base that completely dissociates and breaks into the corresponding ions. Now, how do we relate this to the pH scale? Okay, so the pH scale is going to be the scale that we use to measure how acidic or how basic a substance is. Okay, so it's kind of how we in Celsius we measure, or Fahrenheit we measure the temperature of a body. We're gonna measure how acidic or how basic something is based on the pH scale. Okay, so the pH scale, as I said, it indicates how acidic or basic the solution is, and if the concentration of the hydrogen ions or the hydroxides will vary. Okay, so it's gonna be from 0 to 14. It goes from 0 up to 14. That is the range of the pH scale. Okay, where 7 is going to be what we consider neutral. Now, if you want to mathematically calculate the pH of a substance, you're going to have to use this formula here. The pH of a substance is going to be the negative logarithm of the concentration of protons, of how many protons the substance has, okay? So this symbol that you see here, these brackets that you see here is concentration. That is called the concentration in molarity. Remember the concentration in the ways to measure concentration? So the concentration of the protons is shown like that, like the protons in brackets. So the negative logarithm of that number is going to be the pH of a substance. In the scale, each step of the scale is going to be 10 times bigger or 10 times smaller. So each step that you see here is going to be 10 times higher or 10 times smaller, okay? So for example, a pH of 5 would be 100 times more acidic than a pH of 7, okay? Because there's 2 spots from 5 to 7, okay? So because 5 is 2 spots lower than 7, it's going to be 100 times more acidic, okay? Because remember, when you go down, it's more acidic. When you go up in the scale, it's more basic. Okay, so examples on how to calculate the pH of anything that we have. In order to calculate the pH, as you will just learned, we need to use the formula that we have here. Is the negative logarithm of the concentration of the protons. So if I have to calculate the pH for a solution that has a concentration of protons of 1.0 times 10 to the negative 7, the pH is going to be the negative log of the concentration of the protons. So it's going to be the negative log of 1.0 times 10 to the negative 7. And the answer to this is 7. So that means that this solution is going to be a neutral solution. Okay? If I have to calculate the pH of the following solution, and I know that the concentration is 1.8 times 10 to the negative 5th, that's going to be negative log of 1.8 times 10 to the negative 5th. And the answer to this, you plug the numbers in the calculator, is going to be 4.74. So that means that that solution is acidic. And finally, if I have to find the pH of a solution that has a concentration of protons of 6.4 times 10 to the negative 13th, I plug that in the calculator, I do the negative logarithm of that, and the answer is 12.19. So this solution is going to be basic. Okay, that's for the pH scale. But also we have what we call the pOH scale, which is not so common, but it exists. Okay, so it says that sometimes scientists find it convenient to express the basicity, how basic something is, of a solution using the pOH scale. Okay, so what is the relationship between the pOH scale and the pH scale? The one that you have here. The pOH is going to be the negative log of the hydroxide's concentration, and the pH, the one that we just learned, and the one that we learned right now, plus the pOH all together added up, it adds up to 14. Okay? So again, pOH is the negative logarithm of the concentration of hydroxides, and then pOH plus pH equals 14. So if we know the pH, we can find the pOH, or if we know the pOH, we can find the pH. Okay? So if you know either the pH or the pOH, you can find the other one. So let's practice, okay? First of all, we're gonna find the pOH of these substances and then find the pH once we know that, okay? And then we're gonna learn whether it's acidic, basic, or neutral, looking at the pH. Always acidic, basic, or neutral, look at the pH, otherwise it's gonna be confusing for you. Okay, so let's first calculate the pOHs. The pOH for the first pOH is gonna be, remember, the concentration, the negative logarithm of the concentration of the hydroxide. So that's going to be negative log of 1.2 times 10 to the negative 7. And this gives us 6.92. That is the pOH. And now we find the pH. That remember, pH plus pOH equals 14. So the pH is going to be 14 minus 6.92. And the answer is 7.08. So this would be slightly basic or almost neutral. Okay, almost neutral. And again, if you want to look at how acidic or basic something is, you have to find the pH. Okay, all right. So for the next one, the pOH is going to be the negative log of 8.8 times 10 to the negative 10th. And that gives us a total of 9.05. And the pH is going to be 14 minus that number, because the pH plus pOH equals 14. Okay? So 14 minus 9.05 equals 4.94. And this one is going to be an acidic solution because it has a pH that is lower than 7. And finally, the pOH of the last solution here, it's going to be negative log of 3.2 times 10 to the negative 3rd. And that's giving us 2.49. So the pH is going to be 14 minus 2.49 equals 11.50. That is the pH of the solution, and that means that this solution is going to be basic. Okay, so calculating pH and pOH for strong acids and bases. Okay, remember, what makes an acid be strong or a base be strong is that it completely ionizes, that when it dissolves in water, the ions of that substance break apart, they dissociate, they separate. Okay, so strong acids and bases ionize completely. They ionize completely. Keep that in mind. Okay, so if you want to calculate the pH of a strong acid, you're gonna have to know the concentration of the acid or the base in the solution. Okay, here is the thing. It is asking you, example 7, I'm gonna give you an example. What is the pH of a 0.05 molar hydrochloric acid solution? So hydrochloric acid, we've seen that before, is HCl. It's a strong acid. It's on the list of the strong acids that I gave you before. It breaks, when it breaks into, it dissolves in water, it breaks into H plus Cl minus, okay? That is how we break it. And we actually show the dissociation because sometimes we need to balance. Okay, so it breaks into hydrogen plus and Cl minus. So the question is, what is the pH of this solution? Okay, so in this solution, it's telling you that you have 0.05 molar HCl. If you have 0.05 molar HCl, because this ratio is 1 to 1, you also have 0.05 molar of H plus, okay? And that's why it's important that you balance these equations. Okay, that means that the concentration, this is what matters to us, the concentration of the protons is 0.05. So because the concentration of the protons is 0.05, knowing that the concentration of the protons is 0.05, I can find the pH because I know that that's going to be the negative log of the concentration of the protons. And that's going to be the negative log of 0.05. And the answer to this is 1.3. Okay, so that means that the solution of hydrochloric acid that is 0.05 molar is very acidic. Okay, it's very acidic because it has a very, very, very low pH. Now, the next one, it's going to be very similar. You have the nitric acid, and the nitric acid, HNO3, breaks or dissociates into H plus and NO3 minus. The reason I know this is because I know the polyatomic ions, and let me move this here. So it's because I know the polyatomic ions, okay? And if 0.0063 molar is the concentration of the acid, and the ratios acid to ions or protons, sorry, is 1 to 1, that means that the concentration of the protons is also this number here. So then, because it's 1 to 1, I don't have to do any changes. The pH of this solution is going to be the negative log of 0.0063. And the answer to that is 2.2. And finally, the last question that they're asking you is, what is the pOH? Well, remember, pOH is going to be 14 minus the pH. So 14 minus 2.2. So the answer to that is 11.8. That is the pOH of this solution. It says, calculated the concentration of the protons, of the hydrogen ions, and hydroxides from the pH and the pOH. So far what we have done is you were given the concentration of the protons and the concentration of the hydroxides, and you had to find the pH or the pOH. But now it's going to be the opposite. Now what you need to do is you need to find the concentration of hydrogen or the concentration of the hydroxides based on the pH or the pOH that they're giving. Okay? So in order to do this, you need to just follow these steps over here. So what you need to do is you need to raise the pH to a negative power of 10 to get the concentration of the protons. Okay? So for example, if the pH is 5, the concentration of the protons is going to be 10 to the negative 5th. So raise the pH to negative power of 10 to get the protons, okay? If you want to do the same thing for the hydroxides in the pOH, you will have to raise the pOH to the negative power of 10 to get the concentration of the hydroxides, okay? Let's do an example. So in this example, it says, what is the concentration of a solution that has a pH of 8.9? So the pH is 8.9. So what I want to do is I want to find the concentration of the protons, okay? So to find the concentration of the protons, I have to do 10 to the power of negative 8.9, okay? And that is going to give me a total of 1.259 times 10 to the negative 9 molar. That is going to be the concentration of the protons. Okay? So again, if you do 10 times or 10 to the power of the negative pH, 10 to the power of the negative pH, which is what we learned before, that's what you're going to have to do in order to find the concentration. That is what you're going to have to do in order to find the concentration of the protons. Okay? If you want to find the concentration of the hydroxides, you should do the same thing. Okay? If they give you the POH, the concentration of the hydroxides is going to be 10 to the power of the negative POH. Okay, so we are going to learn now different types of chemical reactions that acids have with either metals or other kinds of substances. Okay, so what this is saying is that acids and bases react in predictable patterns, meaning that when you have an acid that reacts with a metal, you most likely know what's going to happen. Okay, you can predict the products. Though we're going to see 3 cases here, and you're going to learn how to predict the product of how when an acid reacts with a metal, when an acid reacts with a carbonate or a hydrogen carbonate, and when the acid reacts with a base. Okay, so the first example that you're going to see is the example of acids reacting with metals. So the first thing that you need to learn is you need to identify what's the acid and what's the metal, because if you see an acid and a metal together, then you should be able to identify the product. Okay, so if, for example, I have HCl, which is the acid, okay, that is hydrochloric acid, remember, that's the acid. And then I have magnesium, which is in group 2, it's a metal. I know that I have an acid plus a metal. So when an acid plus a metal react, they always going to produce the same thing. They are always going to produce hydrogen gas, and remember the Home 17 rule, so they're gonna always produce H2, and then they are going to produce something that we call a metal salt. And this is what we call the metal salt, because it's a salt, it's an ionic compound that has a metal. That's a metal salt. Okay? So the definition here would be that when metals react with acids, they always form hydrogen gas, as we just said, and a metal salt. Okay? All right, so I'm going to give you a couple of examples. Zinc and hydrochloric acid. So HCl, we just learned that is an acid, right? That is our acid here. And then zinc is a metal, okay? Zinc is a metal. So when you have a metal that is reacting with an acid, the result is always going to be, one of them we know for sure, it's going to be H2, and then we're going to have a metal salt. And that's when this is the most difficult part of this process. What's going to be the metal salt? Well, check this out. If the acid loses the proton, okay, that eventually is going to be here like the H2, okay? So the metal salt is going to be the I'm going to say the product of combining the metal plus whatever is remaining from the acid when it loses the proton. So what's remaining from the acid when it loses the proton? The chloride. What is the charge of this metal? Zinc 2 plus. So when these two combine together, they form the metal salt. And the metal salt is going to be zinc chloride. Okay? All right, one more example. So we have aluminum and hydrochloric acid. So we know that HCl is the acid, and then aluminum is a metal. So because we have a metal plus an acid, we will always form H2, always, and then the metal salt. And the metal salt is going to be the metal plus whatever is remaining from the acid when it loses the proton. So the chlorine, okay? So how do we put these two together? Well, we need to remember what we learned in previous units. Aluminum is always going to be aluminum 3 plus. Chloride is going to always be Cl minus. So we combine these two ions together and we form the metal salt. And the metal salt is going to be aluminum chloride, like this. But now, this is not over, because in every one and each of these cases, the reactions are not balanced. So we need to balance the reactions, okay? So what we do is we go ahead and balance the reactions. So the first reaction to be balanced should have a 2 here. The second reaction to be balanced should have a 2 here. Sorry, it should have a 2 in front of the hydrochloric acid, okay, so that we have 2 hydrogens on both sides. And the third reaction to be balanced, it should have a 2 in front of the aluminum, a 6 in front of the hydrochloric acid, 3 in front of the hydrogen, and a 2 in front of the aluminum chloride. So again, metal plus acid, always is hydrogen, H2, plus the metal salt. And the metal salt is always going to be the metal plus whatever remains from the acid when it loses the proton. Okay, second type of reactions. We've seen this in the past with when we were learning in Unit 7, chemical weathering. Okay, all right, so acids react with metal carbonates or with metal hydrogen carbonates to produce carbon dioxide, water, and a metal salt. So how do we identify these reactions? Well, to identify this reaction, first of all, you need to know what is a carbonate, what is a metal carbonate, or what is a metal hydrogen carbonate, right? So a metal carbonate, okay, a metal carbonate is going to be a carbonate that is made by a metal and CO3. Sorry, yes, CO3. Okay, that is a metal carbonate. A metal hydrogen carbonate is going to be a metal that is combined with HCO3. So a metal hydrogen carbonate is going to be a metal combined with HCO3. So when metal carbonates or metal hydrogen carbonates combined with acids, okay, so in both cases, the first one is with an acid and the second one is with an acid. When they combine with acids, they always form CO2. So you see that on both reactions. Water, you see that on both reactions. And then the famous metal salt, which is the most difficult part to predict of the products, okay? This is gonna be the metal salt for the first case, and this is gonna be the metal salt for the second case. So again, when metal carbonates and metal hydrogen carbonates are combined with acids, they always form CO2, water, and a metal salt. Okay, let's do some examples. So here we have, this is a combination of different problems, okay? In example 4, we have a combination of multiple problems. So we need to understand which one is which, okay? All right, so the first one has an acid, HNO3, this is nitric acid, and a metal. So we're gonna be in our first case here, acid plus metal. So when we have an acid plus a metal, remember, acid plus metal is always going to form hydrogen, and a metal salt. So the metal salt is always going to be, remember, the metal plus whatever is remaining from the acid when it loses the proton. Okay, so in this case, it's going to be the magnesium that forms magnesium 2+, and then the NO3, that is a polyatomic ion, that is NO3 1-. So what's the metal salt? The metal salt is going to be Mg and O3 parentheses 2. That's hydrogen. That would be the answer. Now, is this reaction balanced? It is not balanced. So to balance this reaction, you have to actually write A2 in front of the nitric acid. Now it's balanced. Next one. Next example. We have a metal, aluminum, and then we have an acid, which is sulfuric acid. So when we have a metal plus an acid, again, it's going to be the same type of reaction that we see above. It's going to be, the products are going to be H2, and a metal salt. And the metal salt is going to be the metal plus whatever is remaining from the acid when we remove the protons, okay? So in this case, the metal is aluminum, it forms aluminum 3+, And when we remove the protons, what's remaining from the acid is the SO4 2 minus. Okay, so this is gonna be aluminum sulfate, where the sulfate has a 3 here. Remember the crisscross rule? And the aluminum has a 2 here. And because of that, we need to balance this reaction. So we balance this reaction, and we're gonna have 2 aluminums here, 3 in front of the sulfuric acid, and then we're gonna have a 3 in front of the hydrogen, and that should be it. Okay, next one. We have calcium carbonate. So wait a minute, calcium carbonate is actually one of these two, right? It's a metal carbonate. So we have calcium carbonate here, and then an acid, okay? So when we have a metal carbonate and an acid, remember that the products are always going to be CO2 plus H2O plus the metal salt. And the metal salt is going to be always, and now be careful, it's always going to be the metal plus whatever is remaining from the acid when we remove the protons, okay? So it's gonna be calcium bromide. And to balance this reaction, you know how to balance. To balance this reaction, you just need to write a 2 in front of the hydrogen bromide, the hydrobromic acid. And finally, the last one, we have a metal hydrogen carbonate, so that we're here again. We have a metal hydrogen carbonate with an acid. So again, a metal hydrogen carbonate with an acid will form CO2 plus H2O plus a metal salt. And the metal salt is gonna be whatever is remaining from the acid when you remove the proton plus the metal. So that's gonna be NaCl. And now we'll look at the reaction and we see that it's balanced, so we don't have to do anything else. And finally, the last type of reaction that we're gonna learn here is the acid plus base, super famous in chemistry, okay? So acid plus base, salt plus water, that is the result. It's called a neutralization reaction, okay? So it's a reaction in which an acid and a base react in aqueous solutions, and they produce always a salt plus water, okay? It's a double replacement reaction, remember. So it always produces salt and water. The salt is the metal salt that we've been talking about all the way through here, okay? So example, acid, HCl, base, calcium hydroxide, they combine together and they form the salt plus water. Where does the salt come from? Again, it's gonna be the metal plus whatever is remaining from the acid when you remove the proton. Okay? So next one. Acid, it's going to be HCl. Base, it's the sodium hydroxide. And now this is always going to form acid plus base, salt plus water. So the water, and then the salt is going to be the metal plus whatever is remaining from the acid when it loses the protons. So in this case, it's gonna be sodium chloride. And just to finish, we have the acid, nitric acid, and then we have the base. So acid plus base, salt plus water. So the water, and then the metal salt is going to be the metal plus whatever is remaining from this acid when it loses the protons. So it's gonna be KNO3. And this is the end of notes 9.1.